Good morning, everybody. This is Mr. Steele. I'm here live to you from, I'm here from Saturday, but for you it's Thursday, so in a way you could call this a time warp. But either way, what I am not here. I am probably right at this moment touring Cal State Fullerton, probably being very thankful that I bought new shoes and walking around trying to make sure Ashley and Osfalman don't do anything funny on campus. So, in my absence, instead, I don't want you guys to fall behind because we do have to have a test on this new unit already before spring break. So here we go. We're going to go ahead and begin. The lesson today is going to be about circles, a topic that you've already seen before a little bit back in geometry, but we're going to give it kind of the Algebra 2 treatment and talk about the specific analysis that you're going to need when you graph a circle, as well as how to graph one yourself given an equation, and how to go the opposite direction, vice versa, how to write an equation for a circle given its graph. So it should be very familiar to you. We're going to introduce some important vocabulary though, how to use those vocabulary terms to analyze the circle, and all the individual pieces we need. So our essential question for today is how can we graph and analyze a circle from its equation, and vice versa, because as I said, we're going to be going both direction. And the name of this unit, even though it's not going to be important to you just yet, is conic sections. And basically, the reason we're talking about circles, and then tomorrow ellipses, and then next week hyperbolas and parabolas, comes from the fact that they have a relationship to a cone. We're not going to worry about that too much. You won't really be tested on it, but maybe when I get back from SoCal, I'll make some of those connections, use some of the cool objects in the pod to show you. For now, instead, we're just going to focus on circles. So we just want to be able to graph and analyze circles. So first of all, if I'm talking about a circle, sure, I could just draw and say, okay, what's a circle? That thing. Well, that's cheating. Let's instead use an official term. So what is a circle? Well, a circle I define as a bunch of points. So I'll say all points, a given radius length. So in particular, the keyword is length. So all the points that are a given radius length away from a center point. Okay, so with that said, what I mean is that a circle is all those points that are that distance away. So if we look over here at this circle that we have, the circle is that thick black line going around. Like the key element, like the way we can define what a circle is by looking at a center point and then finding all the points that are that same distance away from the center. So in particular, as you see here, every line that I draw from the center to the edge of the circle is the same. Hence, this is a circle and not some other shape. The defining elements here would be the center and the radius. We'll talk about those in just a second. I'll point them out on here. But first, let's think about then the next piece, which is, well, what does an equation of a circle look like? Because it's not quite as easy. This isn't a function. Obviously, it would fail the vertical line test, so it's not a function. What do the equations look like? Well, for us, just like you saw in geometry, the equation of a circle looks like this. In its most complicated form, I would say, for what we'll see these first couple days. You'll have x minus h squared plus y minus k squared equals r squared. And that's a really cruddy r, so let me try to redraw it. Yeah, there we go. That way Brant doesn't say anything about my r's in my absence. So looking at this, this is actually what the equations of the circles will look like to us. As we look at it, you'll see there's like a bunch of variables in here. The key ones, though, the normal ones, are our x and y. Like those guys are just like normal. Those other pieces, though, the h, k, and r, depend on the circle that we have, and in particular they depend on the two key elements of a circle. They depend on the radius and the center. So first, the center. It's usually really easy to identify when you have a picture like we do at the right. Like the center is just right here. So I'll try to use colors to match it up. That is the center. So I know, let's see, what can I do? I'll just circle it. I'll just color it in. There we go. It's fun to color, just like back in first grade. So the center, that's the point that all those lengths or all those points are centered around. I mean, obviously all those other points are the same length away from that single point. And from an equation, the way we can find the center is it's just h comma k. And what I mean by that would be that those are the two values that make the individual terms here, x minus h squared and y minus k squared, equal to 0. So they make the squared stuff equals 0. That's where each one of those comes from. So again, center is pretty easy to find, especially because if you have an equation already, you can just see the dot. If you if you already have the graph, you can see the dot. If you're given an equation, obviously you can just look here and figure out what makes each one equal to 0. You get your center. Next would be our radius. So let's see, find a good color here. Let's go with blue. The radius, well, from our equation, the radius is just going to be the square root of r squared. So whatever that number is over here, we take the square root, and we'll end up getting what the radius length is. On this circle, we can see the radius length in a bunch of different directions. There's one length, there's another length, there's another length. Oops, that's kind of crooked, but that's okay. And there's another length. We'll notice each one of those lengths is actually 3. So for this circle that we have on our left, our radius length would be 3. But in particular, it'll just always be the square root of whatever number is given on the right side. So very easy to find. It's as easy as taking a square root. And basically, as you can kind of tell in our picture, like, that's pretty much all we have to look for. Like, those are the elements that we need to see in order to graph the circle. Either if we're given an equation, they're the pieces that we need to plot down so that we can graph it, or if we're looking at a circle, they're the pieces that we need for the equation. That's not going to be all that we look at, though, when we analyze a circle. There's actually going to be 2 more elements called the domain and the range, which we'll talk about now. So first, let's start with the definition of all these terms. Let's start with the definition of domain and range. So you have probably seen these before, maybe in Algebra 1, maybe in pre-algebra, it just kind of depends. We'll start with domain. Use a nice hot pink color here. And so what is the domain? Well, it's the set of all the x values that work for a function. So let's put that out in words. Set of all x values. Well, another word for x values too, used a lot outside of math, would be inputs. So I put that in quotes just to remind you that not a technical term. The set of all x values or inputs for a function. And then for us, it's not just going to be that set of all x values, but it's going to be set of all x values for a function written in interval notation. And interval notation is going to be new for most of you, but it's actually a really easy concept to work with. So before we go on to range, which is going to have a really similar definition to domain, you can probably guess what it is. There's just one word that's going to change. We can actually look at this and figure out what the domain is for this circle. It's kind of a cool thing. So basically what we want is we want to know what are the x values that work on this circle. Like where is this circle defined in terms of the x's? Like what's the smallest x and what is the biggest x? Well, typically the way we could do that is with an inequality. So let's take a look once. Like if I look here, the smallest x value that I hit is going to be right over here with that little pink dot. That x value is going to be, looks like -1. Well, that's not right there. We know what it is. The biggest x value that we're going to hit, notice, is if we go all the way across to the far other side. That biggest x value is just going to be 1, 2, 3, 4, 5. So 1 and 5. Where are all the other x values that work? Well, if you notice, if we were to take this circle and like squish it down together into just one line, what we'd have is this. Like it'd be all squished circle. I don't know, might be oozing if circles are made of like slime or something. But that would be what we see. And what you might notice is that thing looks an awful lot like an inequality. And in fact it is. Like think about this. Like what we have here is an inequality, which we could extend in both directions the other way if we wanted to. It starts at -1, and it includes all the x's all the way up to 5. So what our domain is for this function, and I like to kind of do this as like a shortcut. You don't have to, obviously you have a line on your stuff. The domain for this particular circle would be all x's that are a member of. That little symbol means member of. That's what it means. Like we just call it that. It says that x is in this thing. And it says x is a member of, well, everything in that inequality. And that inequality would be -1 less than or equal to x less than or equal to 5. And so yes, this is great. This is one way of describing the domain, but it's not what we want to use. We want to use something called interval notation. And in interval notation, let's see if I can do this right. In interval notation, what happens is we kind of change from focusing on those less than or equal to symbols to using brackets. So interval notation means that closed dots become hard brackets, and open dots, not that we're going to run into them today, become soft brackets. And then what we do is we go from the smaller to bigger. Like basically interval notation always looks like the small number, the smallest one it gets to, comma, the big number. And that says all the numbers between this small number up to this big number. So for us in this case, like trying to describe this inequality in what's called interval notation, we basically just look and see, okay, well my first dot there, it's a nice closed dot because there's function defined there. We can see, well it's not a function, there's graph defined there. It starts at -1. That's the smallest x value we get. And it continues up, including all the x values, up until it hits 5, which is also actually on the graph. And so that is our domain. Our domain is x is a member of, hard bracket, -1, comma 5, hard bracket. And that means the exact same thing as that guy, that inequality. And so what we'll do when we analyze the domain of a function is we'll just look and see, okay, what's that smallest number, what's that biggest number? We'll kind of sketch in the inequality really lightly, and then we'll just translate that into this new interval notation. I know that's really brief, but in fact you'll see for circles and ellipses the next 2 days it's actually really easy to do the interval notation. You're just looking at the edges, the two edges on the horizontal line, and then for the next one, the vertical. So there is domain. Let's move on and let's look at range. Got to pick another color. Let's go with brown. Haven't used brown here. So what is the range? Well, I wish I could just copy the definition and change the colors, but unfortunately I can't. So instead we'll just put it this way. The range is the set of all y values. So instead of looking at the horizontal and seeing what's the smallest x and what's the smallest y or biggest x, we'll look at the y's. So it's the set of all y values, also known as outputs. Again, it's a non-technical term, but you know what it means. Probably recognize it. Set of all outputs for a function, or for a relation, really. I should probably say relation. That's okay, I've already used the word function. And of course, it's again going to be written in interval notation. And again, you might not appreciate interval notation right now. You might be thinking, why don't I just write these things as inequalities? But it's just a preference. Like, we prefer to use interval notation. It looks a little cooler. And hey, if you're hanging at a math party eating pie, you'd want to use the correct notation to describe what's there. So for range, what do we do? Well, I can go right back up to my circle in this example and use it and kind of look at what the range is. What we've got to do first is look for the smallest y. So again, in my mind I'm kind of tracking down from the smallest possible thing I can think of, going up until I hit the circle. And oh, there's the circle. So I'll put my little dot down. That's the smallest y value we hit. And then we have y values all the way up in all of these places up until we hit right there. That's the biggest y value that we actually are going to hit on this circle. In fact, if I draw the thing big enough, what you can see is we have another inequality. It's written vertically, which is kind of weird, but in fact we can do the same thing as before. The smaller number right here is going to be -1, 2, 3, 4. So we've got -4 as the smallest y value it looks like. Then all the ones up in between, up until 2. So for our range, it looks like it would be described by -4 is less than or equal to y's, because all the y's are in between there. Notice we shaded in the middle, going all the way up to +2. And of course we don't like that. For our range, we would want to write it, in this case, in interval notation. So we start it similar to the last one. All the y values that work for our function are included in, or are a member of, well, we've got a closed dot starting at -4, which is kind of smaller, all the way up to 2. And then there would be our range. We're going from smallest to biggest, and that describes all the y values that work for this circle that we're looking at, this relationship here. There are other ways you can kind of look at it, and we'll see them when we get into some of the examples. But with that said, we've now got basically everything that we're going to need in order to graph a circle. We found out what a circle is by thinking about what that actually means. And in fact, if you think about it, like the reason a compass works to draw one is because you set how far apart the pencil is from the set point, and then you spin around. We looked at what the equation for a circle looks like. Again, we haven't seen any examples yet. I'm not going to write the equation just yet for this guy, but we could if we wanted to. We know how the relationship given here in the equation leads us to the center and the radius. Pretty simple stuff, actually. And then we talked about domain and range, not just domain and range, like what they actually mean, but also how we could look at a circle and set up kind of an inequality that describes the x or y values respectively that work for that circle, and then write it in this new thing called interval notation that replaces the shading, sketching, and the less than or equal to gator mouth symbols with hard and soft brackets, or for us here, only hard brackets. So I think we're ready to actually start looking at our first circle. So let's go ahead and do that. So we'll move on to problem number 1 on your sheet. I feel like one of those audiobook operators. Okay, so as our first example here, which you can do right below where you wrote down a lot of the vocabulary, is we're going to go ahead and graph a really simple circle, just to kind of emphasize all the pieces before we move on to ones that ask us to change the center or make the radius hard or look at the domain or range real intensely. So first, let's start with x squared plus y squared equals 16. So very simple equation. Now you might say, hey, wait a second, whoa there. That doesn't look like the equation you drew up here. Right? I mean, look at that, x minus h squared, like there's nothing in there. Well, in fact, that's actually a really nice situation. If there's nothing in there, right off the bat, we can kind of look at it and say, oh, what makes each one equal to 0? Well, what makes x equal to 0? Oh, look, x equals 0. What makes y equal to, oh, look, y equals 0. Basically, right off the bat, we can see from this circle that our center is 0, 0. It's at the origin, which is really nice, because that means we can go over here and plot our little origin, or our little center, right there in the middle. It's not the most circular of centers, but that's okay. Like, that's where all our points are going to start, and then we'll measure our radius length out. Well, to find our radius length then, what we need to do is just look at the equation and check out particularly right over here. Like, we're going to look at this guy for the radius. So my radius is going to be the square root of whatever number's over there. So the square root of 16 is, of course, equal to 4. And so what we do is we count out 1, 2, 3, 4, and that's going to be one radius length over. We'll do the same thing in the left to the back direction, the negative x direction. It's going to be a second one. We can plot another one all the way up, because again, the radius is the same all the way. It's all the points that are 4 away. So there are 4 dots that represent 4 points on our circle. And of course then for the other ones, we don't have to be so specific. We don't need a compass to draw this. We just have to kind of fudge it and try to draw as round a circle as possible. So I'm going to attempt to do that right on here. It might end up being a really good circle. It might not. Oops, I missed. Okay, not the world's best circle. Something you'll learn from me later on is that if you want to cover up the fact that it's hard to graph a perfect circle by hand, just make your dots bigger, and then it's hard to tell. And so, although this isn't perfect, this does represent the circle that we're looking at. So in fact, already just after like 30 seconds, we've been able to graph the circle that we have in question. So hooray us, like we've got our circle. Now the problem is, like even though we have it all done, we still have to finish. We still have to look at what the domain and range are. We're going to use the same things as before, the same notation. So I'll start by reminding myself that domain is always x as a member of, and range is always y as a member of. We're always going to be looking for just the x's for domain and just the y's for range. To find them then, at least when you start out, it's easiest just to start by actually drawing in the inequality. So for x's, I start over here at a place that we'll talk about later describing negative infinity, and then I'll just go along until I actually hit the circle. I'm just like waltzing around like, there's a circle. Okay, so there's my circle. So my first point is right there. What is that value? What is that x value, I mean? Well, that x value is negative 4. From there, notice that as we go this way, if we were to squish this circle down, we'd have graph all the way through here. There'd be some circle hanging around, sitting right along this line until we reach that point. And this point then is our biggest x value. It's the maximum x that we can hit, and that value is of course 4. So our domain is just what's got to describe that inequality. Inequality wise, it's negative 4 less than or equal to x less than or equal to 4, saying it's all the x's are between negative 4 and 4. But in interval notation we use hard brackets. Say the smallest number that x hits, or the smallest x value is negative 4. The biggest one is positive 4. Very easy to look at. Now that's a crappy bracket, so let me fix it. That's a crappier bracket. Looked like I was trying to play hangman or something. There. And so there's our domain. So what about range, you might ask? Or you're probably thinking in your head, well, I guess I could probably do that just as quickly. So in fact, let's do that. So starting in the y's, again, we start all the way at the bottom. We work our way up, going until we hit circle. Ah, there it is. So again, draw my dot really, really big so that way my circle looks like it goes through there. There's the smallest, and then as we go up, notice there's graph to our left and right. Like there's still circle here, so this is all part of the range. We're going up and up and up and up until we hit right there. And there's the highest y value we hit. Well, what are those y coordinates? Well, the smallest one is negative 4 also. Not coincidentally, because our circle's centered at 0. And our biggest one is 4. So for our range, we again use hard brackets. The smallest y value that we hit was smallest y value that we hit is right there. So the smallest one is negative 4, and then on upward to the biggest one, which is right there. And of course, the biggest one is positive 4. We don't have to write the plus, we can just put 4. And yay, oh, that's another bad bracket. That second bracket's hard for me for some reason. There we go. So we've got our domain and range, just by looking at the graph and seeing what those biggest and smallest ones were. So, cool, not bad. Very easy problem. You probably did a problem just like this, maybe even this exact problem at some point during geometry. So nothing really strange or that could really trip you up on that one. We've just used the equation to graph it by figuring out what the center was from right here, what the radius was from right here, and then finding the domain and range by drawing in what the sketches of the inequalities would look like. So one circle down, let's look at example 2 now, which is a little bit more challenging. Okay, so our second circle. Let's see. For our second circle, let's do this one. Let's start adding to this a little bit. So this time, we're going to ask you to graph and analyze the circle. X plus 3 squared plus y minus 1 squared equals 4. So this is not a super challenging circle, so I'm not going to worry too much about pen color now. Looking at it again though, what's changed is now we've moved the center. The center is no longer going to be at 0, 0, because what makes each of those factors equal to 0 is no longer just 0 and 0. So looking at it, we can tell initially what the x value would be by looking at what makes each one equal to 0. So my x values, let's see, what makes this one equal to 0 would be negative 3. It's the opposite of what's in there. So my x coordinate in my center is going to be negative 3. My y coordinate is going to be whatever makes this one equal to 0, and of course that would be positive 1. So my center this time is going to be plotted at negative 3, comma 1. So all the points are going to be the same distance away from this guy right over here. Now second, our radius, well, it should be pretty easy to do. Notice 4, the number on the right side, is a perfect square. So when we find its radius, that would be the square root of 4, which equals 2. So all the points on the circle will be 2 units away. So 1 point will be right up here. 1 point will be right down here. 1 point will be right over here. And 1 point will be right over here. We've got our circle ready. We just now have to draw it in. Well, now actual drawing skill may vary, so let's see if we can do this very well. Nope, that's like a straight line. Jeez. Okay. Okay, it's like really hard to draw a circle on here, but close enough. So there's my circle. Yay, we graphed it. Good job. 2 points on the test. Okay, so we've got the circle, but of course we want to do domain and range. So we want to see those guys also and figure out what is the smallest x value that would work here and what's the biggest one. So let's take a look here, because it's not going to be quite as easy as before. Notice before, since our center was 0, 0, our domain and range, even though one is x, one is y, they both came out to be the exact same set of numbers. They were all the numbers between negative 4 and 4. Now, because our circle's off center, and it's not just centered right smack dab, like bam, right there in the middle of the graph, like we're not going to end up with our domain and range looking exactly the same. They obviously could, but they're not going to. So let's instead think about it for a second. So first, domain and range, they're both going to be x is a member of, and y is a member of. Again, that's just to say which one we're looking at, so you have to include that there to be full credit. You can't just automatically slap down a bunch of hard brackets and go like, bam, got it. That doesn't work that way. Let's look at the x values. So if we start over on this side, our smallest x value is right here. Notice there's no circle over on this side. Then we can squiggle our way all the way across up until we hit there. And that guy's our biggest x value. Now what are those values? Well, let's count from the origin over to see where they are. Negative 1, negative 2, negative 3, negative 4, negative 5. So our smallest one is at negative 5. Our biggest one is at negative 1. So our domain is going to be all those numbers in between negative 5, the smallest one, and negative 1, the biggest one. And notice again that all the circles there, so that if we were to scrunch it down just to a line, we'd see just this guy. Maybe less squiggly, but whatever the case. Now for our range, we're going to have something very similar. So let's look. Where are we? Okay, here's our center. So we're going down 2. So let's see, down 1, down 2. So here's the first point. This as we come up, our smallest value is right there. Then we again squiggle our way all the way through up until we hit this point. And there's our biggest point. What are those coordinates? Well, y-wise, this is negative 1. It goes all the way up to 3. So our smallest value is negative 1. Our biggest value is positive 3. And there we go. We've graphed the domain, or we've found and written down the domain and the range for this circle that we have on the left side. Now something you might notice, a way to kind of check yourself to see if you did it right, is that this should reflect, the same spread, right? Because if we look side to side, this is 1, 2, to the center and then 2 more to the other point, there should be a spread of 4 on the domain between the smallest and biggest numbers. And notice -5 plus 4 is -1. Works out perfectly. That's exactly what we'd expect. They're 1 diameter away, double the radius. On this guy, -1 plus 2 is 3. Once again, they both check. So they both have a spread of 4, a diameter of 4, like however you want to think about it for the circle. And so in fact, our domain looks to be correct. Not only did we use the look at stuff method by looking at this stuff and like actually sketching on the inequalities themselves that represent them, but we can actually just check it by thinking about what we know about a radius and how far apart the edge points would end up being. And there we go. We've again analyzed yet another circle. Yay us. Okay, so what do we have? We've got one more example where something else can be twisted, like something that we haven't seen yet get twisted. So here we go. Okay, so our third circle, like I said, let's see here. You've done pretty much everything up to this point. We've shifted the circle around and everything. But one thing we haven't really messed with is the radius. So let's tweak that radius just a little bit here by writing it as 12. 12. Yeah, yes. Yes, quite excellent. Well, okay, so what are we going to do here? Well, let's start with the simple thing. Let's start with the center, because nothing on this left side is anything challenging. So for the x-coordinate in the center, we look here. What makes that guy equal to 0? In fact, I've been saying that a lot, so maybe I should write it once for those visual people. What makes... I think it's pretty simple, but it's easy to screw up. So what makes that equal to 0? Well, obviously the answer is... I'm assuming you all said the same thing. 2. The answer is 2. Over here, what makes that guy equal to 0? Well, that would be -2. So our center is going to be at the point 2, comma, -2. So right about here. And again, if I make it big enough, like, hey, covered a lot of options. Now the radius. Okay, so we've done the radius before plenty of times. The one thing we haven't seen, though, is a radius that didn't work out really nicely. So, like, here's where we look for the radius. We have to figure out what is the square root of 12. So, r is going to be the square root of 12. Well, that's good, but I mean that's not simplified, obviously. We can still jailbreak that guy. So one thing we want to do to write out what the radius is here is actually do the jailbreak. So 12 is 2 times 2 times 3. So we've got a pair there. One gets out, the other one gets shot, dead, killed, buried, covered up by the warden while he gets a promotion. And there we go. We get that r is 2 root 3. And so over here for our radius, even though it's not a whole number, a nice whole number, we write 2 root 3. Now, of course, then what do we do with the radius? Well, we go to our center and we count out 2 root 3. So, that's a little harder to do than just counting out 2 or 4 or 5 or some really nice number. So instead what we need to do is, if we want to be able to do this, we also need a little bit of an approximation. Like, we need to know about how big 2 root 3 is. And now you can probably do it in your head, because 12 is really close to 9, so the square root of 12 should be close to, but a little bigger than 3. But in fact, we can ask a calculator. So here's my trusty, crappy Windows 7 calculator. It says that the square root of 12 is 3.46. So I'm going to approximate that as about 3.5. And the reason I approximate it is not for anything, like 3.5 is an acceptable answer for the radius, but it is an acceptable way for us to count out where those extra points would be. So I go to my center and I count out 1, 2, 3, and about a half. Again, I'll make my dot big enough that I can justify that I was there. We'll count backwards the same, 1, 2, 3, about 3.5. And again, this is all just kind of approximation. We can't really do that, make it look right to us just yet. 1, 2, 3.5. And then down the same thing, 1, 2, 3.5. And so there are the, kind of the edge points of our circle. So all we have to do is draw it in. I'm not very good at that, but I'll try to draw it. I mean, especially on one like this where you're not drawing the exact distance out. Actually, it might be the best circle that I've drawn. Like, there it is. So again, our circle is just by, we actually plot it, even when the radius is like not a whole number, or not a perfect square. We can get it out there just by going through and, approximating what that radius is. And so for an answer on this line, when the radius isn't nice, I would want an answer like this. I'd want the exact one right here, and then I'd want the approximate one with that little approximate sign. So I would want to see both of them right there. Okay, so there we go. We've got the circle graph. That's all wonderful. Now the thing is, we need to do the domain and the range. And that's definitely a little bit harder than before, because we can't just look at it. I mean, if we look at this thing and think, we go, okay, well, there's the first point. We go and squiggle our way all the way across until we hit this point, and there would be our x's. But the question is, what is this? I mean, we can tell it's about -1.5, and this one is about 5.5, but that's not good enough. Like, we want to know the exact x values that work in this equation. Like, what's the biggest one, what's the smallest one? And unfortunately, like, we don't have that from just looking at it. Instead, what we need to think about is how we get there. So one thing that we've kind of like glossed over because we were using the look at stuff method is the fact that the center and the domain and range are really related. So let's think about this. For a general circle, your center would be h comma k. Right? No debate there. It's just whatever those two numbers happen to be. In this case, h is 2 and and k is -2. So there are h and k. Now the way we find our domain is we count out, like we get those 2 points. Like one's a radius length away in the back negative direction and one's a radius length away in the positive direction. So for our domain, what we're really doing is we're taking the x coordinate here and we're taking it and we're subtracting the radius, and then we're taking that x coordinate of the center and we're adding a radius. Like that's the exact way we counted out. Now remember, we started at the center and then we counted r in this way, r that way, and then for the for the vertical ones we did the same thing. Start at the center, count back a radius and up a radius. So for us here, same thing, range would look kind of the same, except in this case we'd be using the y coordinate. So y coordinate is k, so to find the smaller number we subtract r from k, and for the bigger number we add r to k. So this isn't some new way to find the domain you have to use every time. I mean, if it's a nice perfect square and you can just count out the radius, then just look at stuff. But for this guy, since it's 2√3, it's a little differently, we do need to use this. We're going to have to think about what we are doing. So for example, for the domain here, what is this first value over here? Well, look at it. What we did is we got that first point by taking the x coordinate of the center. So we started at x equals 2, and then we subtracted the radius. Well, that was about 3.5, but exactly 2 square root of 3. That's going to be the smallest x value that actually works. Our 2 that it started at minus, or going back, 2√3. Our biggest one, well, that's just the same. We started at the 2, and then we added 2√3. Again, this is kind of weird, because we're not writing the approximate. Like the approximate would tell us about where they are. This is just the exact x values that it would work at. For range, we can do the same thing. So where did we start? Well, our y coordinate of the center is -2. So we started here, and then we counted back, or down, a radius length. So that's -2 minus our radius length of 2√3. For the other one, we started again at -2. That'd be right here, and then we counted up a radius length. So that's -2 plus 2√3. And now if you were to approximate these, you'd see they come out to be exactly what we would want to do. Like on our thing, let's just do 1 here. Let's see if this works. 2 minus, oh, I guess it doesn't want to do that. So 2√3. Okay, that calculator's kind of a failing here. It's not a good calculator. So instead, you can just take my word for it or pull out your calculator and take a look. That if you do that, this will come out to be the right thing. 2 minus 2√3 is -1.5 up to 5.5, and this one is -5.5, 1.5. So it works out really nicely. So the trick is with a like when you have a radius that isn't a perfect square, the trick is to find the radius exactly like you would anyway, but then approximate it so that you can actually draw out where the graph is, like find out where that circle is and sketch it in. And then for the domain and range, just remember that what you're really doing is you're going r away from the center in both directions, side to side and up and down, and that lets you actually write out what the domain and range are. On your homework, I think there's 1 or 2 maybe that have you do this, so just keep this example in mind when you get there. And so there we go. So there is a third example, and that kind of covers the only other twist you can get in a circle. What happens when this guy's not a perfect square? So just really quickly before I leave, just remember why we even cared. Well, this was not a perfect square. Okay, so here we go. Let's move on. Okay, so for the fourth example, no, just kidding. I'm not going to do a fourth example here. That'd be kind of silly. This is kind of easy. Instead, what I'm going to do is I'm going to give you this as a try it. So go ahead and try to graph this circle, so you know the deal. So after I finish writing out the equation, if you can please pause the video for just a second, while everyone takes a minute or two to try to graph this guy. I'll make it an easy one. So I would like you to graph the circle represented by the equation x plus 3 squared plus y plus 4 squared equals 25. So go ahead and pause the video. So look at this. Oh, look at that pun. Pause. See? Oh, there's just one. I'll put an S at the end to make it plural. Okay, go ahead and pause the video, please, and then take a few seconds to finish this one. Okay, I'm going to assume that you already paused the video, so I'll go ahead and fill in all the stuff here. So for my radius, I'm going to use that as the square root of 25, which is 5. For my center, I'm going to look at what makes each of these guys equal to 0. Clearly, the first one is going to be negative 3. The second one's going to be negative 4. So I'll have my center point as negative 3, negative 4, and then I'll count it out. Back 5, forward 5, down 5, and up 5. So there are my pieces. Now I just have to draw it in. Easier said than done. Okay, not the world's best circle. Oh well. Kind of squiggly over there, but hey, we'll call that a circle. So Brant, don't make any comments. That's a circle. Like, see, I can make sure it's true by saying this. So, get it? It's a circle. Okay, so now domain and range. I'm going to do it a quick way. I can do these in my head. Probably you'll be able to as well. Basically what I do is, instead of like counting it out, since it's kind of hard to count down here, and since my circle looks really crappy, instead what I can do is I can look at my center and go, okay, if my x-coordinate is negative 3, I'm going to go back 5. Negative 3 minus 5 is negative 8. And you notice that is the x-coordinate right over here. It's negative 8. Going over to the other side, well, we can clearly see it's 2. And of course that matches negative 3 plus 5. Negative 3 plus 5 is equal to 2. And so there's our domain. As far as range, let's see. Our y-coordinate of the center is negative 4. We're going to go back 5, so negative 4 minus 5 is negative 9. And once again, notice that the graph actually matches that. Negative 9 is right down here. The biggest one will be this coordinate plus 5. That's going to be positive 1. And again, notice that it matches as well up there. And so there's our circle. It's got a radius of 5, its center is negative 3, negative 4, its domain is all the x values including and between negative 8 and 2, and its y values are all between negative 9 and 1 including those two. And so there is our circle. Hopefully you got 100%. If you did, good job. See, all you need is an electronic version of me. You can figure it all out. Good job. But yes, that's not the only thing we want to do. I want to do one more thing before we call this a day, especially because it's kind of a shorter lesson. So looking at it, what I would like to do is not just be able to have you go from an equation to a graph, but to also be able to go backwards between an equation or between a graph and an equation. So this first guy, we want to go do this thing that I like to call back workwards. It's a very witty way of talking about this. That's basically doing the same thing in a reverse order. So the question is, how can we use this picture of a circle and figure out what its equation is? Well, if you look at it, this actually isn't hard at all. I mean, it's really not bad at all. All we need to do, really, I mean, everything we need to write the equation is actually right up here. This stuff is just for extra practice. So looking at it, we just need to find the radius and find the center. The center part will give us the left side. Like, we need the center so that we can fill in this thing. This part will come from the center. And then on the other side, so I'll change the color just so I can do something entertaining. So the center is going to come from there. On the other side, we're going to need this from the radius. So basically it's just one piece for each one. So let's start with the radius, since that's just one little piece. So the radius. How do I find the radius? Well, I just count from the center, which I'm going to assume is right there. That's why there's a big dot sitting in the middle of the circle. And then it's going to be how far we go from here to the edge. So my radius will be 1, 2, 3, 4, 5, 6. So it appears the radius is 6. Let's make sure, just one more time. Let's go in the other direction. 2, 3, 4, 5, 6. Oh, it is. So in fact, it does look like the radius is 6. If I went up, we'd see that it's also 6. My radius is 6. That means over here, I'm going to put 6, and then it's going to be squared. Why is it squared? Well, because that's how the equation works. Actually, the answer is better than that. It's actually because it's the distance formula. That's what the Pythagorean theorem and all those guys really mean. But, there we go. So we know the radius is 6, so we know that part of the equation. The whole thing at the very end is going to be equal to 36, because that's what 6 squared is. Now for the other part, the center. So we know it's going to need an x and a y in here. The question is going to be what else is going to go there. So I'll switch back to red. And now let's look. So what is my center? Let's start there. What is my center? Well, I start at the origin. Go, okay, my center's right there. That's going to be back 3, so negative 3, comma, positive 2. So negative 3, comma 2 is my center. Well, how does that help me? Well, I go down and go, okay, negative 3 has to make this equal to 0. Negative 3 and then 1 gives me 0. Well, negative 3 plus 3 equals 0. So negative 3, or it has to be x plus 3, because then negative 3 would make it equal to 0. On the other side, the question is, how does 2 equal 0? Well, you subtract 2, so the same thing happens down here. We go y minus 2 squared, and that gives us the left side. So from there, we don't have to simplify in any way, although we could write it out in a standard form instead. But instead, what we have is an equation of x plus 3 squared plus y minus 2 squared equals 36. And we have our equation. Good job. You can go backwards. All we need is the center and the radius. Now, of course, though, we have the domain and range there. We don't want to just leave them hanging. We want to fill that in just like we normally would. In fact, it's easier because we don't have to worry about making mistakes graphing it. And what we can do is we can just go ahead and figure out, well, what are those x and y values that work? So we'll go the old-fashioned way. We'll go over here. You can tell that's going to be 3, 6, 9. So it starts at negative 9, and then it goes all the way over here to positive 3. So my domain is going to be hard bracket, negative 9, comma 3, meaning every number between negative 9 and 3, including negative 9 and 3. And for my range, it will also be hard brackets. In fact, I can set it all up there with a nice little comma. The smallest y value is negative 1, negative 2, negative 3, negative 4. The biggest one, so actually I'm going to put that over there. We always go smallest to biggest. Smallest is negative 4. Biggest one is 1, 2, 3, 4, 6, 7, 8. And there is my domain and range, or there are my domain and range. Notice again, you can kind of check yourself. Negative 3 minus the radius is negative 9. Negative 3 plus the radius is 3. Good. 2 minus the radius is negative 4. 2 plus the radius is 8. We're all good to go. Like, we have our final answer. So very nice. We were able to find the equation of a circle. So go ahead, and at this point, I'll ask you to go ahead and also make this one a triad. Like you saw me do it, you saw where all the pieces come from. So please try to write the equation of the circle as well as complete all the analysis information for this cutesy wootsy little circle over here. Okay, so please pause the video at this time and take a moment to try this one for yourself. Okay, did you try it yet? I'm going to assume you had to try it, and I mean, if you're one of those people who says they tried it and then really didn't try it, that makes you pretty much as bad as a person that graphs a line when they really were supposed to graph a parabola. So, yeah, if you didn't try it, well, you're basically a kid and killer, so keep that in the back of your head. I'll go ahead and do this. So let's just start right here. Let's go left to right, up to down. Let's see what happens. So my radius, well, I can tell right now, it's back 2, up 2, right 2, down 2. My radius is 2. So, lovely. My center, that's going to be positive 2, comma 1, 2, 3, 4. So my center is positive 2, comma 4. My domain, well, I'll just do that now. I'll save the cool part, the equation part, for the very end. My domain, it starts over here. Well, the x value associated with that is 0. And then it goes all the way over to here. So it goes over to 1, 2, 3, 4. That should make sense, right? Because, like, if we double our radius, it should go 4 apart, and it is. For my range, it starts down here. That's at a value, y value of positive 2. Then it goes up 4 units, up to, let's see, make sure, 1, 2, 3, 4, 5, 6. So my range is from positive 2 to positive 6, and everything in between. Okay, as far as the equation, well, I got to use both these pieces of information. So first, this is kind of nice. Like, our center is 2, comma 4. So 2 and 4 have to make the first term and the second term respectively equal to 0. So the first one would have to be x minus 2. It's the opposite of what's there. So x minus 2 squared plus y minus 4 squared. That would make each one equal to 0. Then it's got to equal the radius squared. Well, last time I checked, 2 squared was 4. And so there is our equation. Equation of the circle is x minus 2 squared plus y minus 4 squared equals 4. Now, of course, something I might throw out there just because I'm sitting here at my desk with a tablet staring at the screen on a Saturday, something I might throw out to you is that there is another way to write this equation. You could actually write this exact same equation as x squared. Let's see, I'll just do it right here quietly. Let's let you sit there and think about what it is that I'm doing so quickly in my head so that I can do this. Let's see. So another way that we could talk about this circle would be just like this. the question is, well, like, what does this all mean? Like, what is this thing that we're talking about here? Or actually, you know what, that's not even the best way I could write it. I could probably write it like this. It's probably better. So what's the difference between this equation and this equation? Like, how are they different? Well, I'll tell you this. This is what's going to be called graphing form. We'll talk about it. We always use graphing form when we want to graph the equation. It's just one way to write the equation. The second one down here is called standard form. Sometimes it's also called like quadratic form. Seen it both ways. But either way, basically what I've done is I've taken this this equation, the graphing form equation, and I've multiplied out these binomials. X minus 2 squared becomes x squared minus 4x plus 4. Y minus 4 squared becomes y squared minus 8y plus 16. And it was all equal to 4 anyway, and then I just moved everything over. So the question we're going to have to tackle eventually, not anytime soon and not on your homework today, is how do we, first of all, recognize a circle when an equation is written in standard form. So I still can't draw any sort of round object here. So how can we recognize a circle from an equation like this? And of course, how can we take an equation, if it's written this way, and turn it into a graphing form equation so that we could say graph the actual circle that's represented? Well, those are both going to be questions for later on. So we'll save that mystery for next week. All you have to do for now is graph circles, write their equations, and find this information. So really quickly, to kind of review what we've done today. We started with talking about all the vocabulary that we'll need for graphing these circles. In particular, we talked about what a circle actually is. We looked at what its equation looks like and found that there were really two important pieces of information: the center and the radius. Those are the two that matter the most. We also talked about what domain and range are, as far as like what x values and y values respectively work for a given circle. And then we found a way to write them using what's called interval notation, which uses brackets instead of the little gator mouse. From there we did a couple examples. One of them where the center was 0, 0, which was just x squared and y squared. That kind of showed us how everything worked in a really neat manner. Then we did another one where the center shifted off just a little bit, so we could see how we could look at the graph and figure out what the domain and range are when that happens. Third, we saw what happens when the radius isn't a perfect square. We saw that we do need to approximate it a little bit so that we can graph the circle on the grid just about. Like, we don't have to be exact at all. We don't have to worry if we're exactly 2√3 away, just somewhere in that ballpark of 3.5. Then we saw how we could use the domain and range, or how we could find the domain and the range exactly using that radius, and how we actually plot the points on the circle. Kind of cool. Fourth, you tried a problem. It's pretty easy. I made a pun. Fifth, we went backwards, so we looked at a graph in a circle, the graph of a circle. We analyzed what the center and radius were just by looking at stuff and counting things, counting boxes. We were able to very quickly write the equation. Then you did the same thing, and for no apparent reason, I talked about how the fact that we could actually multiply this whole equation out and have something that represents the same thing but looks way more complicated. And then I told you not to worry about it until next week. So at this point, I'm going to leave you and ask you to please go ahead and, or ask Benton if you could please pass out the homework assignment for them. Spend the rest of the period working on that, or standard quiz corrections, whatever your choice is. And then I won't see you tomorrow. Benton will probably see you tomorrow. I'll be touring 3 more colleges: Loyola, San Diego State, and University of San Diego. But until that time, have a good day. So, just because I like signing my name on this thing, it's always fun. This is Mr. Steele, signing off, telling you to have a nice day in California, in Northern California, while I'm not here. Bye.